Hello again. So we get to the divergence theorem. This is going to be a very useful theorem for calculating surface integrals, which is what we did in the last section. Right? So you can already see that we're going to convert a surface integral into a triple integral or volume integral. Right? Right. So to do that, what we need is a closed surface, right? S. So just imagine some closed surface, right? It could be a sphere, or it could be any blob like this. Again, it's a surface, right? With a unit vector, a unit normal vector, right, that points outward. So at each point, our n points outward. Right. I mean, if it points inward, then this dot product will just give you the opposite sign, right? It'll be negative instead of positive, right? So when you switch the orientation, right, when you go from outward normal to inward normals, that effectively just reverses the sign from minus to plus or plus to minus, right? Okay, so this closed surface, right, is the boundary of a solid region Q. So Q is what's inside, right, the surface here, right? So if the surface were a sphere, then Q would be the ball, right? The ball that's inside. So Q is what's inside the surface S, right? So S is the surface, Q is what's inside. It's the solid region, right? And we have a vector field, right? A vector field F that's everywhere in space, but in particular, right, in the region Q. Right, so every point there's a vector, and that includes on the surface, right? And it doesn't have to be outward, of course, although it could be. Right, some of these vectors might even point tangents to the surface, or might point inward, right? So all these green vectors are just part of the vector field. And I guess my normal vectors were also green, so let me highlight the normal vectors that's not part of the vector field, right? These are, perpendicular to the surface, right? Or normal to the surface, right? Okay. So it's a continuous vector field, and it's even stronger than that. The partial derivatives of m, n, and p have to be continuous. So it has to at least be differentiable, and it's even slightly stronger than that. You take the partial derivatives of m, n, and p, right, with respect to x, y, and z, and all those partial derivatives have to be continuous functions. Okay, which does guarantee that it's differentiable, but but it's being differentiable might not even be enough here. Right. So yeah, the main idea is with all those conditions that this is true. That if you take the surface integral of the vector field F, right, normal to the surface, that it's the same as the volume integral, the triple integral of the divergence of the vector field F. Okay, so that's kind of amazing, right? That what you're doing is you're only, on the left side here, you're only integrating the vector fields that are, on the surface here, right? Has nothing to do with the vector field in Q, inside the surface, right? Underneath the surface, right? So, yeah, so that's just the usual flux integral, right? The flux integral of the vector fields all along the surface. But it's the same as if you take the divergence of the vector field everywhere, so that includes inside of Q, right, that you get the same thing, right? So this is kind of amazing, right? And the proof is in the book. It's about a page. It takes about a page or so, maybe a page and a half to prove it. And, they use a special case, and then you can generalize to other types of surfaces. But the surfaces they use are essentially where you have a function, right, like a dome, So a function of x and y, let's say, and then a cylindrical part here, and then maybe a surface underneath here as well. So they prove it for these types of regions, right? But you can generalize this because every region you can kind of, you know, turn into a bunch of these things, right? And it might take an infinite number of them, but that's for a different course. That's for analysis, right? But generally speaking, the proof for this special case, if you can follow it in the book, that's fine. I'm not gonna do it. I'd rather spend more time doing examples of this than the proof. Okay, so here's our first example. We're given a vector field, right? So this is the vector field xi plus yj plus zk, all divided by the square root of x squared plus y squared plus z squared. In fact, another way to write this vector field is just r hat, right? So it's actually a unit vector everywhere in space except the origin, and it just points outward, right? And its magnitude is 1. So it just gives you some idea, right, of what that vector field is. Q is the ball of radius 2, right? And I wrote it both ways here, right? Either way should tell you what Q is. And then S is the boundary of Q, right? Which means S is just the sphere of radius 2. Well, in other words, it's the set of points x, y, z, such that x squared plus y squared plus z squared equals 4, right? For Q, you have less than or equals. So, of course, yeah, you just have a sphere, which is a closed surface, right, of radius 2. And Q, of course, is the ball, so that's what's inside. And S is just the surface of that. Okay. So we want to calculate the flux integral, right? And in fact, this should not be a difficult flux integral to do by hand. So maybe we'll do it. Yeah, we could do this directly, right? I mean, obviously, the easiest way to do it would be to use the divergence theorem. But let's save that for later, right? Let's do it the hard way first, right? Right. So in the last video, we learned how to parametrize the sphere. Actually, that was 2 sections ago. But we also did this in the last video too, I'm pretty sure. So, right. So S is just, we can describe it parametrically, R of U and V. So R was, this is radius 2, right? So there's going to be a 2 here. And I know I factored out the 2 last time, but I'll keep it here. So sine of U, cosine of V, and then 2 sine U sine V, and then 2 cosine of U. And U goes from 0 to pi. And V goes from 0 to 2 pi. Okay, so that's the sphere, right? And we need the partial derivatives, right? Because we need this NDS. So we'll take the partial derivatives yet again. So with respect to U, we're going to get 2 cosine U cosine V, 2 cosine U sine V, and then negative 2 sine U. And then the V partial of R, it's going to be negative 2 sine U sine V, and then positive 2 sine U cosine V, and then 0, right? So remember the flux integral over the surface S is the double integral over the region R of f dot ru cross rv, and then dA, which we can just use du dv here. And, well, because of that, we know r is just the rectangle. U goes from 0 to pi, and v goes from 0 to 2 pi. All right. So, yeah, we calculated this cross product before. And maybe we'll do it again because, of course, I forgot it by now. Oh, and what's f? I guess we need to know what f is. F is the vector field here. Right. Right, so in terms of u and v, this looks like it's going to be quite a hassle here. But if you notice, the denominator, square root of x squared plus y squared plus z squared, is just 2, because that's the radius, right? Right, and then the numerator, xi plus yj plus zk, is, well, it's just r itself, right? It's just this, right? Right, this is x, this is y, this is z. So putting that together, that just cancels the 2's, right? The denominator is also 2. So this is just the vector sine u cosine v. Oh, no 2. We divided by 2, right? Sine u sine v, and then cosine of u. Okay, so that's the vector field f. Just making that clear. And now we take the dot product with the cross product of these two vectors here. And like I said, I don't remember what it is, but it's going to be, let's see, 4. So we'll factor out the 4 here. I got to remember we did that, right? Sine squared of u cosine of v. Sorry, that's supposed to be a v there. Right, and then positive 4, so I factored out the 4, sine squared u sine of v. And then the last one is going to be 4 times, let's see, sine u cosine u. Can I squeeze that in? Right, and then du dv. Sorry, I'm running out of space here. I guess I can move this a little bit. And then du dv, right? Okay, now just take the dot product. And looks like we get a bit of a mess here. We're going to get sine cubed of u times cosine squared of v, right, plus another sine cubed of u, but now we get sine squared of v, plus sine u times cosine squared of u, du dv, right? And you can already see, at least I hope you can see this, that for the first two terms here, right, you're just going to get sine cubed of u, because when you factor out the sine cubed of u, you just get cosine squared plus sine squared of v, which is just 1. So, yep, this is just sine cubed of u. Right. Plus sine of u cosine squared of u. And we can factor out another sine. In fact, I guess we could have done this all at once, but I didn't see that until now. So factor out another sine of u, and you get sine squared of u plus cosine squared of u, right? So if, like me, you were a little worried about the sine cube, like, oh, now I got to look up the formula. Nope, it's, right, this is 1, so you're just integrating sine of u after all that. du dv, right? And the integral of sine is, well, negative cosine. So I'll pull out the negative. The dv, of course, will just end up being 2 pi here. Oh, right, so cosine of u from 0 to pi. And I think that's just going to be negative 2, right? It's negative 1 minus 1, right? So negative 2 times negative 4 is positive 8 times 2 pi. So I think in the end we just get 16 pi. So I think that's the value of this flux integral, 16 pi. Okay, well, right, that was the hard way. Now let's do it the easy way. Oh, I think, so I just realized something. I think I wrote down the wrong problem, but okay. That's okay. Right, so the easy way would be to calculate the divergence of this vector field and then integrate that over the solid region, right? So that'll be doing a triple integral, which, you know, you might think might be more difficult, but if you look at this wasn't exactly easy here. It was a lot of algebra mostly. All right, so yeah, so let's take the divergence of the vector field F. All right, so I just copied down the vector field, and now to take the divergence, right, that's just the dot product of del and F, or partial of m with respect to x plus partial of n with respect to y plus partial of p with respect to z. Right. So I'll write this out in all its rather gory detail. So we're taking the partial of x with respect to x of x divided by the square root of x squared plus y squared plus z squared. Oh, yeah, I guess I'll write them all down. But you'll see that each one is very similar. So once you do the first term here, you can pretty much guess at the other two terms. They're more or less identical, just using a different variable in the numerator, right? Right. So, yeah. So using the quotient rule, we get the denominator squared, which is, oh, get rid of the square root. So it's just x squared plus y squared plus z squared. Right. So then you get the denominator times the derivative of the numerator. So that's going to be the denominator, squared to the power 1/2, and then the derivative of x is 1, minus numerator times the derivative of the denominator. So that's going to be x times 1/2 times 2x times x squared plus y squared plus z squared to the negative 1/2. Right. Plus, and then we'll do the other terms later. So kind of a mess here. But if you multiply top and bottom by the square root of x squared plus y squared plus z squared, you just get, well, x squared plus y squared, sorry, kind of a mess, x squared plus y squared plus z squared, minus, and then the 1/2 and the 2 cancel, so you still get x squared times 1, right, all divided by x squared plus y squared plus z squared, but we multiplied by that to the 1/2, so this is to the 3/2. Plus dot dot dot, right? So the x squared minus x squared cancels, and you just get y squared plus z squared all over x squared plus y squared plus z squared to the 3/2 power. So you see what happened here, right? The denominator is going to be the same for all of these partial derivatives. The numerator will just exclude that variable, right? So without having to go through all this again, we can see that the second partial derivative, the one with respect to y now, will just be x squared plus z squared, right? Because it's going to be y squared minus y squared, right? Divided by x squared plus y squared plus z squared to the 3/2. Oh, let's just write it down here again. It's supposed to be y. Right. And then the last term will just exclude the z squared, so you'll get x squared plus y squared, all divided by the same square root. Well, square root of x squared plus y squared plus z squared cubed, right? So when you add up all the numerators, you get x squared plus x squared is 2x squared, right? Plus y squared plus z squared plus z squared. So you just effectively get 2 times x squared plus y squared plus z squared, right? All divided by x squared plus y squared plus z squared to the 3/2. And now you can see what happens when you subtract the exponents. You just get 2 divided by the square root of x squared plus y squared plus z squared. Right. In other words, just 2 over r, where r is the distance from the origin, right? Yeah, remember we're not using rho anymore, so officially this should be 2 over rho, but we're calling it r now. All right, so that's the divergence. Now all we need to do is take the triple integral of this quantity here over the ball of radius 2. Right? So I'll write it out explicitly. dv. Right? And now we should switch to, well, it looks like spherical coordinates here, right? Because it is a sphere. So the usual range, 0 to 2 pi, 0 to pi. And then the radius was 2, so 0 to 2. This is going to be 2 over r. And then the Jacobian for spherical coordinates is r squared sine phi dr d phi d theta. Yeah, I know this looks weird because it used to be rho squared sine phi, but we're changing rho to r now. Now, that's you just have to get used to that. Okay, but this should not be hard. There's no theta dependence here, so you get 2 pi. And there's no phi dependence, right? So you get, I'm sorry, it's the integral of sine phi, right, which is negative cosine phi. So cosine phi evaluated between 0 and pi, I guess we just get 2 there. So now we get 2 times r, right? So now we just integrate from 0 to 2 of 2 times r dr. And that's just r squared, right? So we get 2 pi times 2 times r squared evaluated between 0 and 2. So that's 4 pi times 2 squared is 4 minus 0. So 16 pi. Okay, got it. Yeah. That was the same 16 pi that we got for the flux integral. But here we did it by using the divergence theorem. Right. And on the one hand, you might think, well, that wasn't much easier. I had to calculate the divergence. That was kind of a nuisance. And, I took these little shortcuts here, right? Yeah, it turns out, we could have done this a little bit more simply if you know the divergence in spherical coordinates. Remember that the vector field is just the unit vector r pointed outward, and there's a very quick way to get that in spherical coordinates. But since we don't know the divergence in spherical coordinates, we had to do it using rectangular coordinates, so that was a bit of a hassle. But I think in terms of just the triple integral itself, right, doing the integral itself you can see was, at least in my opinion, much easier than doing the double integral here. So yeah, generally speaking, doing the triple integral is usually easier. I don't want to say always, not always, but in most cases it's slightly easier. And in some cases it's much easier. Right. In this example here, I would say it's slightly easier. Okay. Anyways, yep, so that's the divergence theorem. Again, very useful for calculating flux integrals. Right, we did it both ways. We calculated the left side, and we got 16 pi. We calculated the right side, we got 16 pi. So, right, that doesn't prove the divergence theorem, but at least it shows that it's true for this particular case. Right, so it doesn't contradict the divergence theorem, which is good. That would be kind of a shocker since it's been proven. But you do have to pay attention to the conditions, though, right? That, in particular, the vector field, right, has to have continuous partial derivatives in Q, and well, right, we ended up taking all those partial derivatives way down here, partial of, right, m with respect to x, and of course with respect to y and z as well. These will all be continuous, right? Although there is an issue here, right? Notice that the sphere contains the origin, or not the sphere, but the ball contains the origin. And what happens at the origin? You're dividing by 0. Right? So the divergence has a singularity at the origin, singularity at 0, or at 0, 0, 0, right? Yeah, that's an issue. Technically it's not continuous there. So this was not guaranteed to work out, right? Because the vector field really did not exist, or so it doesn't have continuous partial derivatives in Q itself. Yeah, so that's kind of an issue here. But it worked out nonetheless. At least I think it worked out. Looks like I did it correctly. And we got the same answer. So yeah, I kind of thought that might be the issue when I kind of recognized that here. The original problem was supposed to be the ball minus the unit ball, right? So the radius was only supposed to go from 1 to 2, not from 0 to 2. And in that way, you're not including the origin here, right? It's not part of the region Q. But, that said, it did work out both ways here. All right, well, that's one example. We should probably do another one. Okay, so here's our next example. We're given a vector field F, which is just the vector field xi plus yj plus zk. So it's very similar to the previous example, except it's not a unit vector, right? It's just the vector r itself, right? Not the unit vector. So the further out you go, the bigger x, y, and z, the bigger the vectors, right? Or the bigger the magnitude of the vectors, anyways. S, the surface, is the torus, parametrized by this parameterization, which we've seen before, right? In fact, I think just a few sections ago, we calculated the surface area using this parameterization, right? And I forgot what we got. I think it was something like 4 pi squared times AB or something like that. Yeah. So in some sense, we've already done a very similar calculation before for the flux integral, right? So the question is to evaluate the flux integral of this vector field, but using the divergence theorem. Okay, so in other words, we're not going to calculate the flux integral directly. We could, and it would take a while, right? If you remember the one we did for the surface area of the torus, it's similar to that. But hopefully, by using the divergence theorem, all we have to do is calculate the volume integral over the solid region Q. So the Q is the donut part itself, right? The torus is the surface of the donut, right? The glaze, if you will, just the surface of it, right? But Q is the inside of the donut. Okay. Of the divergence of the vector field F, right, over that volume. Right. So first of all, the divergence of this vector field is about as simple as it gets. Right. So m is just x, so partial of m with respect to x plus partial of n with respect to y plus partial of p with respect to z. Right. So m is x, so this is the partial of x with respect to x. N is y, so partial of y with respect to y, plus the partial of z with respect to z. So you get 1 plus 1 plus 1, which of course is 3. So we're just going to be integrating the number 3 over this volume, right? And in fact, you can take the 3 outside, right? And this, of course, is just the volume of the torus. Volume. Well, okay, so the word torus could refer to the surface of the torus or what's inside. Right, so let me say it's the volume of the solid torus, right, the solid donut. Okay. So unfortunately, we calculated the surface area. We didn't calculate the volume. So now we have to calculate the volume of the torus. So yeah, the biggest problem here is that we don't know what dV is, right? This is not a sphere, right? And the u and v, these are not spherical coordinates, right? Not exactly, right? They're angles. U and v are angles, right? But they're not the same as phi and theta, at least not exactly. So, yep, so we have to calculate the Jacobian for, I don't know what you call it, toroidal coordinates? Yeah. Toroidal coordinates. Right. And, well, there's 3 of them, right? There's u and v, those are the angles, but there's also the distance, right? So for the distance, we're just going to use r, the distance from the origin. So this will be r, u, and v, right? And again, r is just the square root of x squared plus y squared plus z squared. Yeah, that'll work. All right, so yeah, we want to go from x, y, and z, right? Rectangular coordinates, right, to r, u, and v. Right. So yeah, again, this is x, this is y, this is z, and maybe I'll write those down because we're going to need those in just a minute here. Right, so x is just going to be, oh, I think we need to multiply by r. Oh, I take that back. I don't think r is going to be the distance here. Okay, so it is, right, so yeah, forget what I said here. R is not the distance from the origin. It's the distance from the center of the torus, right? So, right, so here's the torus, and remember, if you take a cross section, right, you get a circle over here, and A is the distance from the origin to the center of the circle. B, right, was the radius of that circle. Since we have to go, right, so the surface of the torus is this, but we need to go from r equals 0 to r equals b to get inside the torus, right? So yeah, so effectively r will be the distance from the center of the torus. Okay. And so yeah, so r will be between 0 and b. Okay. Anyways, I don't even know if it's worth going through this, but to get dv, we need the Jacobian. So it's going to be the partial of x, y, and z, the determinant, right, in terms of r, u, and v. And it's going to end up being r times a plus r cosine of v, right, dr, du, dv. Right. So that'll save us a lot of work here. You know, if you want to go through it, be my guest, right? So here's the Jacobian as a determinant, right? It's the partial of x with respect to r, partial of x with respect to u, partial of x with respect to v. And then the second row, right, will be partial of y with respect to r. Am I getting this right, or am I transposing this? Let's see, the rows are the gradients, right? So the gradient of x. That makes sense. Yeah, I think I have it right. So then the partial of y with respect to u, and then the partial of y with respect to v. And then the last row will be partial of z with respect to r, partial of y with respect to u, and I'm sorry, partial of z with respect to u, and partial of z with respect to v. Right. Yeah, so you have to replace the b's with, well, here, let's write it down, right? So x is going to be a plus r cosine of v, cosine of u, I think. Let me check that. Yep. And then y is going to be a plus r cosine v sine u. And z is just going to be r times sine of v. So, right, take all three partial derivatives of all three of these, x, y, and z, and when you take the determinant, you should get this. All right. Right. So I would encourage you to work that out. On the other hand, if you don't, just take my word for it. This is what you get. So now, to do the volume, all we have to do, volume of the solid torus, right, is just going to be the triple integral. So r goes from 0 to b. Oh, I think we want to do r first, right? So u and v both go from 0 to 2 pi, and r goes from 0 to b. So this is r times a plus r cosine of v dr, du, dv. And let's see what we get. For the first integral, with respect to r, we're going to get a times r. So that'll be 1/2 ar squared plus 1/3 r cubed times cosine of v, and evaluated between 0 and b. So, yep, I think we'll just get 1/2, sorry, 1/2 ab squared plus 1/3 b cubed cosine v, and then minus 0, right? So now we do the du integral. That's this one here. Well, yep, first one's just a constant, so we get 1/2 ab squared times u. Oh, and the second one's just a constant. Okay, so 1/2 ab squared plus 1/3 b cubed cosine of v all times u. And then just evaluate u between 0 and 2 pi. So you're going to get a factor of, no surprise, 2 pi. Right. And finally, now we do the inside integral. With respect to v. Yep, so we're going to get, let's see, 1/2 ab squared times v, and the derivative of, the derivative of sine is cosine, so we just get 1/3 b cubed times sine of v, evaluated between 0 and 2 pi. All right, so 2 pi times, let's see, 1/2 ab squared times v, v is just 2 pi minus 0, right? And then sine of 2 pi is 0, sine of 0 is 0, so that term is just 0. So what do we get? We get 2 pi times 2 pi, 4 pi squared, but divided by 2, so 2 pi squared times ab squared. Right. So this, remember, is the volume of the solid torus Q. Right. And that wasn't quite the answer because, right, they wanted the surface integral here. Using the divergence theorem, we had to multiply by 3 because the divergence was 3. Okay. So, yeah, so using the divergence theorem, this surface integral should be 3 times the volume, 2 pi squared ab squared. So we should get 6 pi squared times ab squared. Right, and we got it by computing this thing over here, the triple integral of the divergence. The divergence just being the number 3. It's just a constant in this case. And then just figuring out the volume of the torus, which, you know, that was the bulk of the work here. And in fact, I made it easy by just giving you the Jacobian for these toroidal coordinates, whatever they are. Right. Anyways, yep, that's the second example. And you might wonder, wouldn't it be just easier to do this surface integral, this flux integral, directly? I don't know, possibly. You know, you have to calculate the normal vector, right? So in other words, you have to calculate both partial derivatives of this with respect to u and with respect to v. And I think we did that already, you know, a couple sections ago when we calculated the surface area. But yeah, I'm not exactly sure. I certainly don't remember them, right? Right. Then you got to take the cross product of those partial derivatives, and it's a mess. I don't think it's any easier than this. It might not be that much more difficult, but yeah, let's look. You know, the vector field is certainly continuous. It has continuous partial derivatives. It's about as nice as it gets. So the divergence theorem certainly applies here. And so as long as you trust the divergence theorem, the flux integral will give you the same answer as the volume or triple integral. Okay, next example. Okay, so our vector field now is yi plus zj plus zk. Okay, so this is definitely not the radial vector, right? So up until now, all our vector fields basically just pointed outward from the origin, right? The first one was just a unit vector pointing outward in all directions, right? Like this. And then The second one, right, multiplied by r, so you got, right, longer vectors pointing outward the further out you go. But they were all radially outward vectors, right? So this vector field is definitely not that. Okay, for one thing, it doesn't depend on x, and for another thing, right, it's just not x, y, z. It's not the radial vector. S is the sphere of radius 4, Q is the ball of radius 4, and we want to evaluate the flux integral using the divergence theorem again, right? In fact, if you look at the previous video, the previous section, we did this already, right? We did this already, and this was not a pleasant calculation. It's one that when we got the, right, when we ended up with the iterated integral, it was sine cubed of u, cosine v. It was a mess, right? And I just ended up plugging it in on a computer algebra system because it just seemed so arduous to have to work that out by hand. So in the end, it was a very difficult calculation to do this, right? Made slightly easier by using a computer, right? Right. So that we did already, and maybe I'll remind you, or if you missed it, that we got the value 256 pi over 3. Right. So that's the answer. Now we just have to figure it out. Okay. And again, we're not going to calculate the flux integral again. We're going to calculate the volume integral over the ball of radius 4 of the divergence of f. Okay, so before we do the integral, let's just calculate the divergence of f. It's the partial with respect to x of m is y, plus the partial with respect to y of z, plus the partial with respect to z of z. Well, that's just 0 plus 0 plus 1. So the divergence here is just the number 1. Okay. Oops, triple integral of the number 1. Well, that's even easier than the last one, right? Last time we got the divergence was the number 3. We had to multiply by 3, right? But since we're integrating 1, this is just the volume of Q. Right? And we can either work it out, or you probably remember the volume of a ball of radius r is just 4/3 pi r cubed. Well, here r is, the radius is 4, right? So this is going to be 4 pi over 3 times 4 cubed. So that's going to be, let's see, 64 times 4 is 256 times pi over 3. And there's the answer. Same answer, right? And it, well, I mean, it just took a few lines of calculation here. Mostly just had to calculate the volume of a ball of radius 4. Right? So, yeah, if you remember what a pain it was to calculate this flux integral directly, I mean, it probably took up like a whole page, or at least half a page of work. And in the end, I still used a computer to calculate the double integral, the iterated integral. And yeah, so much easier, right? Way easier. Now, if you, let's say you forget the volume of a ball, well, then you just have to work this out in the usual way. And I feel like we've done this many times already. And the radius is 4, right? So this is r squared sine phi dr d phi d theta. Or if you want to use rho, that's fine too, right? But remember, we're switching to r here. All right, so I'll leave it as rho, I guess, right? So you're just going to do the 3 separate integrals, 0 to 2 pi d theta, 0 to pi sine of phi, and then 0 to 4 of rho squared So you're just going to get 2 pi times 2, and then times 1/3 4 cubed. Right. So again, that's the same 256 pi over 3. Okay. So yeah, if you forgot how to find the volume of a ball, you just work it out again. No big deal. So even doing this, right, is still much less work than calculating the flux integral directly, which we did last time, right? And I specifically said, well, we'll see this example again, and here it is, right? So yeah, so you can see that the divergence theorem really does save us a lot of work in this case, right, and in many cases as well. There probably are situations for which the flux integral is easier than doing the triple integral, the volume integral, but those are pretty rare. I would say those don't come up very often. Okay, another example. So now E is the vector field, right? We can use F. We're using E here. I don't know why. Could be an electric field maybe, right? So x squared y times I plus 3yzj plus 2xzk, right? And Q is, well, it's this region here, and I think we can graph it pretty easily here. Right? X goes from 0 to 3, y goes from 0 to 3, and z goes from 0 to 3. So you should recognize this as just a cube, right, with each edge being 3 units long. Let me see if I can do that. Yep. So length, width, and height are all equal to 3. So it's a cube, right? And S is the boundary of the cube, right? So Q is the solid cube, right? Think of like a die you roll in a game, right? I forgot how they're labeled, right? 1 to 6, right? It's a usual die, right? And if you have 2 of them, you have a pair of dice, right? So the surface of the cube is S, right? And Q is what's inside the cube. All right, so we want to evaluate the flux integral of this vector field, this vector field E over that surface of the cube. So it doesn't say how to do it, right? It doesn't say we have to use the divergence theorem, although we probably will, right? Because to do this surface integral directly is a little bit of a nuisance. Right? Remember, a surface integral, right, consists of, right, the surface of the cube here. And this is not a smooth surface, right? It has edges, right? It has the edge and it has corners. It's not smooth. However, it does consist of smooth parts, right? Piecewise smooth pieces. And each piece is just it's just a square, right? However, there's 6 sides to the square. So, so each surface, let's say the top surface here, right, is just a square, 3 and 3, right? But that's just the top, right? There's the bottom, right? There's the right side, there's the left side, and there's the front and the back. Let's say the back is red, front is red. So 6 sides to a cube. So that means you're going to have to split this up and do, right, 6 separate surfaces here. Right? 1 for each surface. 1 for each square. Right? And again, each square might not be that hard to do, right? To do a, to do the surface integral over the top probably doesn't take that long. And if that's all you had to do, then that would be pretty easy. But you have to repeat it for all 6 of them. Right? And notice the vector field is not going to be the same on all 6 pieces, on all 6 squares. So it's likely that you're going to have 6 separate integrals to do. Right. So this is really where the power of the divergence theorem comes into play here. It's one solid cube. So if we take the divergence of the vector field E, right, over that cube, that's probably going to be an easier calculation than trying to do 6 separate surface integrals, in my opinion. Right. So first of all, what's the divergence of E? I think I can squeeze that in here maybe. Or we can even do it way up here. Right. So it's the partial of m with respect to x. So that's just 2xy. Plus the partial of n with respect to y, that's 3z. And then the partial of p with respect to z, that's just 2x. Okay, so not a trivial function here, 2xy plus 3z plus 2x. So that's the integrand, right? That's the thing we're integrating here. 2xy plus 3z plus 2x, right? But this is a cube, right? It's a rectangular solid. We might as well use rectangular coordinates, dz, dy, dx, where z just runs from, well, here they are, 0 to 3, right? And y runs from 0 to 3, and x runs from 0 to 3. Okay, so this is just an iterated integral that you might have seen way back in chapter 14, right? So at this stage, this should be pretty easy to do, but let's do it step by step, right? So the first integral with respect to z, we get 2xyz plus 3 over 2 z squared plus 2xz. And then, yep, we'll just plug in 0 and 3 for z. Okay. So 2xy times 3 is 6xy plus 3 times 3 squared is 27, so 27 over 2, plus 2 times x times 3 is 6x. Right, so now we just have to integrate over y. Right, so that's this inside integral here. And then we'll have one more with respect to x, right? So integrate with respect to y. You get 3xy squared plus 27 over 2 times y plus 6xy, and then plug in 0 and 3 for y. So 3 times x times 3 squared is 27x, plus 27 times 3, so 81 over 2. And then 6 times x times 3 is 18x dx, right? Well, look, 18x plus 27x is, I want to say, 45x. Right. So when you take the integral of that, you get 45 over 2 x squared plus 81 over 2 times x, and now just plug in 3 for x. Okay, so we're going to get 45 times 9. Let's pull out my calculator here. 45 times 9 is 405. And then 81 times 3 is, I think, 243. But let me check that. Yep. And then 243 plus 405 is 648. Divided by 2, 324. Okay, so that's the value of the flux integral. Had we calculated it directly, again, it's as bad as this was. I would contend doing the 6 separate surface integrals would have been even worse. But you should get the same thing guaranteed by the divergence theorem. So once again, the divergence theorem saved us a lot of work. Rather than calculating all 6 of these flux integrals directly, doing one single volume integral, even though it's 3 separate integrals, it's still easier than 6. Well, right, remember, each surface integral will turn out to be a double integral. So you're probably going to have to do 12 integrals here. And here we only did 3. So yeah, easier in my opinion. Okay, so here's a more abstract theoretical example, right? We're supposed to prove that the surface integral of the curl of f, so the curl of f is a vector field, right, over that surface, or a closed surface S, and any C2 vector field f. So this C2 just means that for m, n, and p here, that m, n, and p have continuous second partial derivatives. Right. But you can see, right, that's more than a mouthful. So mathematicians usually love to abbreviate things, and we just call it a C2 vector field, right? A C1 vector field just means that it has continuous first partial derivatives, right? And, a C3 vector field would be continuous third partial derivatives, and so on. All right, so it's a nice vector field, right? It has continuous partial derivatives. So, yeah, so how are we supposed to prove this when, we can't just use an example of a vector field. We have to show that this is true for any such vector field, right? So the way I would do it is use the divergence theorem. Right. So this is our vector field. In this case, it's the curl of some vector field f dot n ds. But the divergence theorem says that, again, as long as f is a nice enough vector field, and it certainly is here, we can take the volume integral of the divergence of that vector field. But here the vector field is not f, it's the curl of f. And if you remember way back in the first section of the chapter, we talked about this very briefly, I think at the end. The divergence of the curl is just 0, right? And that's true for any vector field with continuous partial derivatives. So yeah, the divergence of the curl is always 0. So what are we doing? We're integrating the number 0, which of course gives us 0, and that's all we had to show. So it's really just a 2-line proof, right? Just write down the divergence theorem, and then use the theorem that says that the divergence of curl is always 0. So that's it, right? So not hard to show, but again, you kind of have to know what you're doing. You have to realize that, oh, since I can't calculate this flux integral directly, I'm going to have to use a theorem, and in this case, the divergence of the curl is what gives you the 0. Right. So not a hard problem, but it's we don't do. In my opinion, we don't do enough proofs in this class, but it's not an analysis class, right? It's not an advanced calculus class, so most of what we do are computations, and because that's what you're going to need in your physics classes, your engineering classes, right? So, yeah. But again, a useful theorem, the divergence theorem, also for proving things, and here's one example of that. Okay, one last example, because, well, we've done plenty of examples where the surface was a sphere. We did a cube, so those are rectangular coordinates, so we might as well do one in cylindrical coordinates because the surface is going to be a cylinder, right? And I added the word closed here, right? So it's a closed cylinder of radius 2, right, and height 5. So that looks about right. Oops. Oh, I made it worse. All right, close enough, right? It's a cylinder, right? So since it's a closed cylinder, that includes the top and the bottom, as well as the cylindrical part, the side, right? Yeah, height is 5. So that's the surface. And notice it's 3 separate parts. It's the cylinder, it's the top, and the bottom. So if you were to evaluate this directly, sure, you would have to evaluate it for the bottom, the top, and the cylinder parts. Oops, I was going to do f dot dA. It's f dot n ds plus the top plus the cylinder part, which, should I just call that the side? Yeah, so this is the side, this is the top, this is the bottom. Right. And again, each one of these is probably not that difficult. But then to have to do all 3, a little bit of a nuisance, right? So let's just use the divergence theorem and take the divergence of this vector field f, which we've done already. So I'll let you think about that again, because, right, we've used this vector field before once, a couple examples ago, right? Yeah, now Q is the solid cylinder. That's the best way to describe it. Solid cylinder. So yeah, it's just a set of points, x, y, z, such that x squared plus y squared is less than or equal to 4. So the radius is 2, right? And z is between 0 and 5, right? Because the height is 5. Okay, right? Or if you want to use cylindrical coordinates, right? R, theta, and z, right? R is less than or equal to 2, and z is less than or equal to 5. So same thing. Oh, and theta, of course, goes from 0 to 2 pi. Right, because you want the entire cylinder, you're going all the way around. So that's an angle of 2 pi, as usual. All right, so yep, the divergence, of course, is just 3, because it's the partial of x with respect to x plus the partial of y with respect to y plus the partial of z with respect to z. So 1 plus 1 plus 1 is 3, if you remember that. And so pull out the 3, the factor of 3, it's a constant. We just need to find the volume of the cylinder. Right, and you probably remember the formula for the volume. I certainly do, but let's work it out anyway, right? This is one that we've done many times before. So theta runs from 0 to 2 pi. Let's see, r runs from 0 to 2, and z runs from 0 to 5. And for cylindrical coordinates, we get r dz, dr, d theta. But yeah, here we have to be careful, right? R is not the distance from the origin. R is the square root of x squared plus y squared. Okay, so yeah, we're using r for 2 different things here. And it's just the context, right? Because we're in cylindrical coordinates, we know we're using this version of r and not the spherical version of r. You know, and if you really don't like the confusion, then just don't call it r, right? Call it rho, like we did way back in chapter 11 and in chapter 14 too, I think. Yeah, but here, so right, r is the distance from the z-axis, right? It's the distance. I don't want to call it the radial distance, but the distance from the z-axis, right? Right, this distance here. Okay, good. Yeah, so this could not be any easier because most of these, right, you're just going 3 times the integral from 0 to 2 pi d theta, the integral from 0 to 2 of r dr, and the integral from 0 to 5 of dz. So that's just 3 times 2 pi times, so we get 1/2 r squared, and we got to plug in 2 there. And then we get z evaluated between 0 and 5, so that's just 5. So yeah, 1/2 of 4 is 2, so we get 3 times 2 pi times 2 times 5. So that looks like 10 times 6, 60 pi. Okay, so that should be the flux integral as well, 60 pi. Oops. I'll put the answer here. Right, so again, we haven't been giving units for any of these. Right, the units are in terms of what the vector field is. If it's the gravitational field or the electric field, you'll have different units. And then for, you know, it's times an area, right? So whatever the field is times an area, those are going to be the units, but we're not worried about that here. You know, your physics instructor will tell you what the correct units for flux is. Okay, yeah. So again, the divergence theorem probably saved us a lot of work here. On the other hand, maybe we should do this directly, right? Because I don't think we did a cylinder in the last section, in the last video. So I think we can probably do this, right? So we're gonna do this both ways. We're gonna do it. We did it the easy way using the divergence theorem. Now let's do it the hard way of just calculating the flux of each of these, right? So again, here's the cylinder again, the surface of it. We have the top, the middle, and the bottom. And remember, the vector field was just x, y, z, right? And so let's do the top first. F dot n ds. Well, what's ds here, right? If this is the top surface, this is just a disk, right? The top is the disk of radius 2. Right? The height was 5, the radius is 2. So your normal vector, of course, remember this has to point outward. So our normal vector here has to point upward. Right? So that's just the vector k. Right? So this is going to be a double integral of the vector field x, y, z, dot product with 0, 0, 1, right? And then ds is just, well, dA, which is dx dy. Although, because it's a disk, we'll probably use polar coordinates. So the integrand here is just going to be x times 0 plus y times 0 plus z times 1. We're just integrating z. And yeah, let's switch to polar coordinates, right? R dr d theta. R just goes from 0 to 2, and theta goes from 0 to 2 pi. Now, the question is, what's z? Well, right, this is the top surface, so z is going to be 5 everywhere on the disk. So z is 5. 5 is a constant. That can come outside. And when you integrate r, you get 1/2 r squared from 0 to 2. So that's going to be 5 times 4 over 2 is 2. Times the theta part will just give you 2 pi. So I think that's going to be 20 pi. Okay, so that's just for the top. Now we have to do the bottom. And for the bottom, of course, because the normal vector has to point outward, our n here will be negative k. Although I don't think that'll actually matter that much here. So f dot n ds. Right. So f is the same. It's just going to be x, y, z. But now the dot product is with 0, 0, negative 1. And I'll just use dA here. So now our integrand is just negative z. But this is the xy plane. Z is 0. So we're just integrating 0, which gives us 0. So 0 for the bottom, 20 pi for the top. And now we just have to do the cylindrical part, right? This part here, right? Yeah, so that probably will be the most difficult part, but I don't know, maybe we did one like this before. I don't remember. So here's the vector field F. Right, so now the tricky part is this is a cylinder, right? So we have to parametrize the cylinder, the surface of the cylinder. And if I remember right, we did that already. So maybe I'll just remind you. We did that by using, let's see, so the radius is 2. So 2 cosine of u, 2 sine of u, and then v for the height. So u goes from 0 to 2 pi, and v, which is the z here, just goes from 0 to 5. Okay, so take the two partial derivatives. With respect to u, you get negative 2 sine u, 2 cosine u, and then 0. And then the derivative with respect to v, we get 0, 0, 1. And so the cross product, Ru cross Rv, that'll give us the normal vector, right? Right, it's going to be 2 cosine u minus 0, and then 0 minus negative, so positive 2 sine u, and then minus 0, and then 0 for the last one, right? Right, so that's my n, that's my, vector n. Now it's not a unit vector, but to make it a unit vector, you could just divide by 2, right? Yeah. On the other hand, if you do the vector field f dot, right, this vector here, dot little n, it works out, right? So let's do it that way. So what are we integrating over? U goes from 0 to 2 pi, and v goes from 0 to 5. So we'll do du dv here. And the vector field, oh, I need more space, is just x, y, z. So x was 2 cosine of u, y is 2 sine of u, and z is 0. And take the dot product with this vector here, 2 cosine u, 2 sine u, and then 0, du dv. Okay. So for the dot product, we're going to get 4 cosine squared u plus 4 sine squared u plus 0 times 0, right? But that's just 4, right? 4 times cosine squared plus sine squared is 1. And yeah, this is just du dv now, right? So this should be 4 times 5 times 2 pi, which is 20 times 2, 40 pi. And that's for the side. Okay, so remember now we just have to add them all up. Bottom plus top plus side. So bottom plus top plus side. The bottom was 0. The top was 20 pi. Was it? Yep, 20 pi for the top. And then the side was 40 pi. So 20 pi plus 40 pi is 60 pi. And look at that. That was the same answer we got by doing the divergence theorem and just doing the triple integral. So once again, the divergence theorem seems to work. And, well, at this point, right, you tell me which way you prefer to do it. Do you want to do the surface integral or the flux integrals directly? Then you got to do all this, right? Or would you rather just do the divergence theorem and just do a single, well, a triple integral, right? So 3 integrals, but it's just 1, right? So we did 3 integrals here to get the 60 pi. And here we had to do 3 separate surface integrals. Each one was a double integral, so we had to do 6 integrals. So probably twice as much work to do it directly, just evaluating the flux integral as we did in the last section, right? Without using the divergence theorem, yeah, this is a bit of a pain. But we got the answer. And of course, we got the same answer using the divergence theorem. And probably a bit easier using the divergence theorem. Right, so that should do it, right? So in this section, you're going to be either doing flux integrals again, or more, maybe a couple of them for the homework. They might want you to do it both ways, right? So get a little bit of practice doing it both ways, maybe one or two of these. But most of the problems that you're going to be doing in this section, you want to convert to the divergence theorem and use the divergence theorem. So convert to a triple integral, and that will generally save you a lot of work. Right. Oh, and by the way, we could have saved ourselves even more work had we known the volume of a cylinder, right, is just, well, right, pi r squared h. So the radius is 2, and the height was 5. So 3 pi, that's supposed to be a pi, times 2 times 5. R squared, right? 3 times 2 squared, sorry. Yeah, so 4 times 5 is 20, 20 times 3 is 60, so 60 pi. Right. So that would have saved us the trouble of working out this triple integral. And that, then it would have been almost too easy to do it that way. But like I say, this works out both ways. All right, so enjoy doing the homework for the divergence theorem.